NENOMATICA, where mathematics meets YouTube excellence. In this example, we will use symmetric expressions in the roots of a quadratic. The goal is to compute x1 squared plus x2 squared without solving the quadratic directly. Here is the example. Let s equal x1 plus x2 and p equal x1 times x2. For ax squared plus bx plus c equals 0, we have s equals negative b over a and p equals c over a. Using our coefficients a equals 2 root 2, b equals 3 root 2, and c equals negative 1, the sum s becomes negative 3 root 2 over 2 root 2, which simplifies to negative 3 over 2. For the product, p, we compute negative 1 over 2 root 2. We rationalize the denominator by multiplying by root 2 over root 2 to get negative root 2 over 4. Next, we use the symmetric identity for the sum of squares. x1 squared plus x2 squared equals the square of the sum minus 2 times the product. That is s squared minus 2p. Now substitute s equals negative 3 halves and p equals negative root 2 over 4. We square negative 3 halves and subtract 2 times p. This becomes 9/4 plus root 2 over 2. In this example, we will evaluate the symmetric expression involving the roots of a quadratic. We will follow the exact algorithm shown, compute the sum and the product of the roots, then manipulate the target expression step by step. Here is the problem. We are given the quadratic x squared minus 4x plus 1 equals 0. We want the absolute value of square root of x1 minus square root of x2, where x1 and x2 are the roots. Step 1. Using Vieta relations, the sum of roots s equals 4, and the product p equals 1. Now write a as the absolute value of the difference of square roots. Square both sides to eliminate the absolute value and radicals inside the difference. Expand the square of a difference. Replace the sum x1 plus x2 by s, and the product x1 x2 by p. Take the principal square root of both sides to solve for a. Substitute s equals 4, and p equals 1. Since the square root of 1 is 1, simplify the inside. Finally, for minus 2 equals 2, so a equals the square root of 2. In this lesson, we will evaluate a symmetric expression in the roots of a quadratic. We are given the quadratic x squared minus 4x plus 2 equals 0. Let x sub 1 and x sub 2 be its roots. Our goal is to find the value of the quantity square root of x sub 1 over x sub 2 plus square root of x sub 2 over x sub 1, following a clean step-by-step algorithm. Step 1. Let a denote the given expression. We square a to remove the radicals. So a squared equals the square of the sum of the two square roots. Step 2. Expand using the formula. A plus b squared equals a squared plus 2ab plus b squared. That gives x sub 1 over x sub 2 plus x sub 2 over x sub 1 plus 2 times the square root of the product. Step 3. Inside the radical, the fractions cancel to 1. The square root of 1 is 1. So a squared equals x sub 1 over x sub 2 plus x sub 2 over x sub 1 plus 2. Step 4. Combine the two fractional terms over a common denominator, x sub 1 times x sub 2. That gives x sub 1 squared plus x sub 2 squared over the product, plus 2. Step 5. Introduce the symmetric sums s equals x sub 1 plus x sub 2, and p equals x sub 1 times x sub 2. We use the identity x sub 1 squared plus x sub 2 squared equals s squared minus 2p. Step 6. From the quadratic x squared minus 4x plus 2 equals 0, Vieta's formulas give s equals 4 and p equals 2. Step 7. Substitute these into our expression for a squared. A squared equals 16 minus 4 over 2 plus 2, which simplifies to 8. Finally, take the positive square root for the magnitude of the expression. Therefore, a equals the square root of 8. Example. We will solve for the parameter m in a quadratic when the reciprocals of the cubes of the roots add to 2. We are given that x1 and x2 are the roots of x squared minus 2x plus m equals 0. We must find m such that 1 over x1 cubed plus 1 over x2 cubed equals 2. First, recall Vieta's formulas. For a monic quadratic, the sum of the roots s equals 2, and the product of the roots p equals m. Next, we convert the sum of reciprocals of cubes into a single fraction, and then express its numerator in terms of s and p. 1 over x1 cubed plus 1 over x2 cubed equals x1 cubed plus x2 cubed divided by x1 x2 quantity cubed. Using the identity x1 cubed plus x2 cubed equals s cubed minus 3sp, we obtain the compact form s cubed minus 3sp over p cubed. Now substitute s equals 2 and p equals m, and impose the given value 2. We get 8 minus 6 m over m cubed equals 2. Clear the denominator and rearrange to a cubic equation in m. This yields 8 minus 6 m equals 2m cubed, or equivalently 2m cubed plus 6m minus 8 equals 0. Try small rational numbers. Plugging in m equals 1. 2 times 1 plus 6 times 1 minus 8 equals 0. So m equals 1 is a root. Factor the cubic by m minus 1 to get m minus 1 times quantity 2m squared plus 2m plus 8. The quadratic factor has discriminate 2 squared minus 4 times 2 times 8, which is negative 60, so it has no real roots. Therefore, the only real value of m that satisfies the condition is m equals 1. In this lesson, we will derive a compact formula for a symmetric expression in the roots of a quadratic. Here is our setup. x1 and x2 are the roots of x squared minus sx plus p equals 0, with x1 greater than x2. Our goal is to find m x1 squared plus n x2 squared in terms of s and p only. From Vieta relations, the sum of the roots is s, and the product of the roots is p. We will also use the difference of the roots, which equals the square root of s squared minus 4p, because the leading coefficient is 1. These three facts will drive the entire derivation. The key trick is to rewrite m times x1 squared plus n times x2 squared as a combination of the symmetric pieces x1 squared plus x2 squared and x1 squared minus x2 squared. That split isolates a perfectly symmetric part and a perfectly antisymmetric part. First, compute x1 squared plus x2 squared. That equals the square of the sum minus 2 times the product, which is s squared minus 2p. Next, compute x1 squared minus x2 squared. Factor as the difference of squares, which is x1 minus x2 times x1 plus x2. Substitute the facts to get south times the square root of s squared minus 4p. Now substitute both results back into the split expression. The symmetric piece becomes 1/2 times m plus n times s squared minus 2p. The antisymmetric piece becomes 1/2 times m minus n times south times the square root of s squared minus 4p. In this lesson, we will evaluate a symmetric expression in the roots of a quadratic. The roots x1 and x2 satisfy the equation x squared minus 4x minus 2 equals 0. We will compute a complicated ratio built from powers of the roots, step by step. Here is the problem. Since x1 and x2 are roots, each one satisfies the quadratic. Move the constant term to the other side to get x sub I squared minus 4x sub I equals 2, for I equals 1 and 2. This lets us simplify each cubic expression in the denominator. Therefore, the denominator is the product 2x1 plus 3 times 2x2 plus 3. Expanding gives 4 times x1 x2 plus 6 times the sum x1 plus x2 plus 9. Now rewrite the numerator by factoring out x1 x2. We get x1 x2 times x1 cubed plus x2 cubed minus 3x1 x2. Next, use the identity for a sum of cubes x1 cubed plus x2 cubed equals the sum cubed minus 3 times the product times the sum. Introduce the symmetric sums. Let capital S equal x1 plus x2 and capital P equal x1 times x2. From the quadratic coefficients we have s equals 4 and p equals negative 2. The quadratic coefficients we have s equals 4 and p equals negative 2. Substitute into the numerator and denominator. The numerator becomes p times s cubed minus 3ps minus 3p. The denominator becomes 9 plus 6s plus 4p. Plug in s equals 4 and p equals negative 2. Evaluate each piece carefully to avoid sign mistakes. Compute the numerator. 4 to the third is 64, and 3 times negative 2 times 4 is negative 24. So the bracket is 64 plus 24, which is 88. Negative 2 times 88 is negative 176. And adding 6 gives negative 170. The denominator is 9 plus 24 minus 8, which equals 25. Recap. We use the fact that each root satisfies x squared minus 4x equals 2 to linearize the denominator. We rewrote the numerator with the sum of cubes identity, introduced s and 2 to linearize the denominator. We rewrote the numerator with the sum of cubes identity, introduced s and p, then substituted s equals 4 and p equals negative 2 to evaluate the expression exactly. In this lesson, we will evaluate a symmetric expression in the roots of a quadratic. The roots x1 and x2 satisfy the quadratic 2x squared minus 3x minus 3 equals 0. We want the value of capital A equals the quantity x1 minus 3 squared plus x2 minus 3 squared. First expand each square using the binomial pattern. Now, gather like terms. Combine the x1 squared and x2 squared terms, the linear terms, and the constants. Introduce the symmetric sums. Let s equal x1 plus x2 and p equal x1 times x2. Then x1 squared plus x2 squared equals s squared minus 2p. Substitute these into the expression. From the quadratic 2x squared minus 3x minus 3 equals 0, the sum of the roots is negative b over which equals 3 halves. The product of the roots is c over which equals negative 3 halves. Substitute s equals 3 halves and p equals negative 3 halves into the expression. Compute each piece step by step. As a quick numerical check, the roots are 3 plus or minus square root of 33 all over 4. Evaluating the expression with approximations produces about 14.25, which matches 57 over 4. Recap. In this lesson, we will evaluate the symmetric expression square root of x1 plus square root of x2, where x1 and x2 are the roots of the quadratic x squared minus 19x plus 9 equals 0. We'll follow a clean, step-by-step path that uses Vieta's formulas. Step 1. Let it be the sum we want. A equals square root of x1 plus square root of x2. Step 2. Square both sides to remove radicals in a symmetric way. A squared equals the quantity square root of x1 plus square root of x2 squared. Step 3. Expand the square. That is x1 plus x2 plus 2 times square root of x1 x2. Step 4. Use Vieta's formulas. For a monic quadratic x squared minus sx plus p equals 0, the sum of the roots is s and the product of the roots is p. Here s equals 19 and p equals 9. Step 5. Substitute s and p into the expanded expression. A squared equals s plus 2 times the square root of p. That becomes 19 plus 2 times the square root of 9. Step 6. Evaluate the square root of 9, which is 3. So a squared equals 19 plus 6, which is 25. Step 7. Since square roots are non-negative and both roots of the quadratic are positive, a must be positive. Therefore, a equals the positive square root of 25, which is 5. Conclusion. The value of square root of x1 plus square root of x2 is 5. Example. We will use symmetric expressions in the roots of a quadratic. Let x1 and x2 be the roots of the equation x squared minus 19x plus 9 equals 0. We will find, first, a which is the square root of x1 plus the square root of x2, and second, the value of x1 cubed minus x2 cubed. From Vieta's formulas for ax squared plus bx plus c equals 0, the sum s equals x1 plus x2 equals negative b over a, and the product p equals x1 times x2 equals c over a. Here it equals 1, b equals negative 19, c equals 9. So s equals 19, and p equals 9. Part A. To find a which is the square root of x1 plus the square root of x2, square a to remove the radicals. A squared equals x1 plus x2 plus 2 times the square root of x1 x2. Replace x1 plus x2 with s and x1 x2 with p. That gives a squared equals 19 plus 2 times the square root of 9. So a squared equals 19 plus 6 equals 25. Since a is positive, a equals 5. Part B. Now compute x1 cubed minus x2 cubed. Use the difference of cubes. X1 cubed minus x2 cubed equals x1 minus x2 times x1 squared plus x1 x2 plus x2 squared. Rewrite the second factor as x1 squared plus x2 squared plus x1 x2. But x1 squared plus x2 squared equals s squared minus 2p, so the whole factor becomes s squared minus p. For a quadratic, x1 minus x2 equals the square root of the discriminant over a. Here the discriminant delta equals b squared minus 4ac, which is 325, and it equals 1. Therefore, x1 cubed minus x2 cubed equals the square root of 325 times s squared minus p. Plug in s equals 19, and p equals 9 to get the square root of 325 times 19 squared minus 9. That equals the square root of 325 times 352, or, simplifying the radical, 1,760 times the square root of 13. Summary. We use Vieta's formulas to express everything in the symmetric combinations s and p, and the discriminant for the difference of the roots. The results are 8 equals 5, and x1 cubed minus x2 cubed equals 1,760 times the square root of 13. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.